let's go ahead and summarize the kinematics equations that we have so far. So we've got our one for position, got delta x equals v naught t plus 1/2 a t squared, have v equals v naught plus a t. And finally, what we have is our one that's true all the time, just our general definition of average velocity. Delta x equals the average times t. So these are the main three that we've been using so far, and if these were the only three that you ever used for the rest of your life, you'd be set. However, I will derive one more for you that you will find helpful for certain cases where you don't have information about time at hand. You have to have some other information as well, but in some situations, this last equation will be much more useful and straightforward to use than these three. Of course, it does derive from these three, so again, these three will cover you if these are the only three that you ever use. But let me give you one more. So let's go ahead and rewrite some of the information that we have. Let's try and solve for t and see if we can come up with an equation where our t does not appear, where we just have information about our distances, our speeds, and our acceleration. So we're going to take this middle equation here. We're going to say v equals v naught plus at, and we're going to solve for t very simply. So we have t then is equal to v minus v naught divided by a, right? Change in velocity divided by your acceleration, that will give you your time. So this is how we can rewrite time. Another thing that we can do quickly is we can rewrite our average velocity. So how else can we rewrite average velocity? So the way we can do this is we can say this. V average is also going to be able to be written as v plus v naught divided by 2. So this is if a is constant, right? So this one is true if a is some sort of constant value, which again, for almost all the problems that we're doing, that will be true. And so if that's true, right, if we're just accelerating at a constant rate from one speed to the next, what we end up showing is this, right? It's just a straight average of our final velocity and our initial velocity. Just add them together, divide by 2. Of course, all we're really saying here is, again, if you accelerate from 0 miles per hour at a constant rate up to 10 miles per hour or whatever, however fast you might be going, your average speed during that time, your average velocity during that time, will be 5 miles per hour, right? It would be halfway in between those two, right? It works even if you're not starting at 0 velocity as well. If you accelerate from, say, if your initial speed is 30 miles an hour, and you accelerate up to 50 miles an hour, right? Add these together, divide by 2. Your average speed will be halfway right in between, will be 40 miles per hour, right? So again, if the a is constant, that will hold true. So with these two, then we can go ahead, we can go back to our third equation here. Again, this one is always generally true, but we are going to say, okay, let's use it in the case where a is constant, since that basically covers all the situations that we will cover for the problems that we'll be solving. So let's just say we have a as constant. Let's substitute in our t and our v average in this equation here. And then that will let us write something where t does not appear, and we can simplify it from there. So we have delta x equals v average. Wherever I see the v average, I'm going to plug in this. So I have v plus v naught divided by 2. Now I have my times t, and my t that I derived from our velocity as a function of time equation is going to be v minus v naught divided by a. So this might look a little bit ugly at first, but we can actually simplify this into a very useful equation here relatively quickly. So let's write it like this. So we're going to have delta x, oops, there we go, delta x equals 1 over 2a times v plus v naught times v minus v naught. So I'm basically just saying, okay, I have these two terms here. 2 times a, I'm going to pull that off to the side. It's 1 over 2a. Make sure to remember that part. And now what I have is this ugly expression here, but we can actually simplify this very easily. We can do our FOIL method. We can multiply this through. But what you'll see is that you do have this v plus v naught and v minus v naught, right? This ends up being the result of a difference of squares. In this case, the squares that you're dealing with are, of course, going to be v and v naught. So it'll look like this. X equals 1 over 2a times v squared minus v naught squared. So from here, I'll multiply both sides by 2a. So I have 2a delta x is equal to v squared minus v naught squared, and this looks much more manageable. So the way that people usually actually write this, you can write it however you want. This is totally valid. The way it's usually written, the way you'll see it in your textbook, and the way you'll see it usually when people are summarizing the 4 kinematics equations that we deal with, they will write it like this. Our v final squared is equal to v initial squared plus 2a delta x. Right, and so now we have our final velocity related to our initial velocity, our acceleration, and our distance, and nowhere in this equation does time appear. Again, of course, we had to, if you go back up and you look at how we actually derived this equation, of course, the time is kind of hidden in there. We just kind of solved for it, excuse me, in terms of different variables, right? So this will be our 4th kinematics equation. So then we can come back up here. We can say, okay, let's add this to the list. So we have these 3, and we will also say v squared equals v naught squared plus 2a delta x. And so all of these equations that we have here will be, you pretty much do every single kinematics problem that we will ever do in both 1 and 2 dimensions. We haven't done 2 dimensions yet, but these will actually apply in 2 dimensions. We'll have to make some sort of changes. We'll have to specify some other things a little bit more. We'll have to be a little bit more careful about it, but we will be using these equations in both 1 and 2-dimensional kinematics. If this is your starting point for any of those problems, you can basically solve any kinematics problem that you could ever think of.